Hello, everybody. Welcome to B-Sides this morning. Hope you're having a great time. We're going to hear from Chris this morning on abusing WCF endpoint for RCE and privilege escalation. Take it away, Chris.
All right, guys. Thanks for coming to my talk. Yeah, we are going to be talking about WCF endpoint exploitation. And just real quick, want to thank the organizers and the volunteers for putting on the con. Like my first B-Sides was last year, and it's a lot of fun and an honor to be up here today. So my name's Chris Anastasio. I'm a pen tester at Illumint. I'm co-founder of a little hacking group in Palo Alto called Dark Corner. I have a couple certifications, and I'm into stuff outside of hacking, but honestly, this is like my main interest. It's just what I love to do. And if you asked me when I was a kid what I wanted to do, it was pen tester, so I'm very happy. But the agenda for today is going to be a brief intro into WCF. We'll look at target enumeration, so finding software to try to exploit. We'll look at an example vulnerable service and then some real-world examples and have a demo. Sorry, I'm kind of nervous, but my motivation for this talk came after my friend presented his research around WCF. After getting a bunch of CVEs in VPN clients and some network monitoring software, I read his work and I wanted to go find my own bugs along the same lines. The other thing is I want to get the word out about WCF as an attack vector because I haven't really seen many people talk about it, and it seems like it's a pretty ripe vector. A lot of the software that I've looked at, it's been really easy to find bugs and easy to exploit them. So what is WCF? It's short for Windows Communication Foundation, and it's a platform for developing service-oriented applications. So any application with like a client-server model, and the service, receives a message from the client and will take some action based on that message. And the communications can take place over a number of protocols. The most prevalent that we've seen in real life are raw TCP, HTTP, and name pipes. So WCF services are defined with an address, binding, and contract. The address is just a URI. It looks pretty familiar, and it'll have 3 or 4 parts depending on whether or not there's a port. And so we have the scheme, host, port, and path. And bindings just specify the transport protocol for the communications. So again, we'll have like TCP or HTTP, and then the encoding scheme could be text or binary. And you can optionally configure transport security. There are a ton of bindings, but again, those are the most common that we've seen. And then the contract, it defines what functionality is actually going to be exposed by the service. And so you can identify the contract by the service contract attribute in the code. And then the operation contract attribute gets applied to whatever methods are going to be exposed through the service. So the contract's where the bugs are going to be. The issue here is not with WCF itself, but the fact that the applications are exposing powerful operations over WCF. Sometimes in my experience, I've seen that there are attempts to lock down access to these operations, but they can be bypassed. And also, when you're looking at these operations, exploitability may not always be straightforward. An example was like you could modify the VPN config for a VPN client. So it's not direct code execution, but you can stick a line in the config that when you connect using the VPN, it's going to run a command as system. So not always straightforward. So target enumeration, We're looking for .NET binaries. WCF was released with the .NET Framework 3.0. And for local targets, we're going to be focused on processes running as a privileged user, like local system or local service. Now, local system is a lot less privileged than, local service is a lot less privileged than system. But there are ways like Rotten Potato that will let you escalate from service to system. And then for remote targets, the service has to be using a network binding, like NetTCP binding. I see these are more often using net name pipe binding, so it's going to be only locally exploitable, so just for PrivEsc. But you can use Process Explorer to identify the .NET processes that are running on your system, just to highlight them. And then also in Process Explorer, if you click on properties for a process, you can look at all the loaded .NET assemblies, and you want to look to see if system.service model is referenced, because that's got all the types and classes needed to build a WCF service. So beyond Process Explorer, you can use the WMI command line, and I have a little one-liner here that queries for all the running services on a system, and then we'll just run findStir in a loop against each service binary and look for the string mscore.dll. This is a key dependency for any .NET binary. It can be prone to false positives and negatives, but for the most part, it's been reliable when I'm using it, and it has the advantage of working using only native tools. And so it's easy to run it against, like if you're doing an internal pen test, it's easy to just run that one-liner against every system on the LAN. And so I did that the other day, actually, and you can see I got a huge list of .NET services. And if I wanted to, I could trim the results by, instead of searching for mscore.dll, I could search for service model or net.tcp. And the trade-off there is that I might miss stuff, but the advantage is that not only if service model does show up, it's a really good chance that it's a WCF service and not just a .NET service. And if I find the net.tcp string, then it's most likely got some kind of remote service, so higher chance of finding RCE. So now we're going to look at WCF service, which is a forked version of one made by Versprite, which I just made to be remotely exploitable, and it'll help us understand the analysis and exploitation workflow. So analysis begins with decompilation of the target application. And .NET binaries are really nice for static analysis because they decompile cleanly into source code with variable names and comments and everything intact. And I use dnspy, which is an open source .NET decompiler, assembly editor, and debugger when I'm doing this stuff. So after decompiling it, again, we want to check for a reference to system.service model. If we don't find that reference either in the first level of references, or it could be nested inside of another. But if you don't find that anywhere, then the app is not using WCF and you can move on. So the next thing is to find the contract so that you can see what kind of operations, what kind of functionality is exposed by the service. And in WCF service, we see the service contract attribute is applied to an interface called iVulnService. It can be applied to classes or interfaces, but I've only ever seen it used with interfaces. And then the operation contract is applied to the runMe method. And so then we have a class that implements the interface and actually defines the logic for the method. And this one is just going to run a client-supplied string as an operating system command. And then we have the main class, which inherits from service base, which is used to create Windows services. And you'll always find the onStart method is overridden, and this is where you'll find usually the address and binding information. So here we have the address. It's net TCP binding listening on localhost port 81, and the path is vulnservice/runme. And because it's using net TCP binding, it'll be exposed over the internet. And also, binding security has been disabled. So by default, net TCP binding requires credentials of type Windows. So you're going to have valid creds to connect to the service. But we'll look at a real life example later on if there's time where they did exactly this and the security mode was set to none. So then there's a call to add service endpoint, which consumes the address binding and contract to actually deploy the service. And so if you find calls to add service endpoint, that'll help you get the information that you need to actually connect to the service. So to exploit the service, we need to write a WCF client. First thing, add a reference to system.service model. Next, define the contract. And we can just copy paste this from the service. And we don't actually have to implement the method, like any logic in the method. Visual Studio will actually automatically generated that implementation that just throws the not implemented exception. So it'll do that for you automatically. And so WCF clients communicate over channels, and we can use the channel factory class with the address binding and contract to create a client object that can then be used to actually invoke methods on the service. And so here we're calling runme and passing it calc.exe. And so we'll take a look at a video of what that looks like. So on the left-hand side, there's a Windows 7 virtual machine. The service has been started, and I have Process Explorer highlighted on the service itself. On the right-hand side is the Windows 10 host machine, where I'm going to run the exploit, and you'll see calc get spawned as a child of the service. And it's just going to run a couple more times, and you'll see more calcs. Okay, so now we're going to look at some real-world vulnerabilities. And again, we're looking for bugs in the application logic. There's not a problem with WCF itself per se, but whatever functionality's been exposed through it. And the issue here seems to be that developers aren't considering the idea that rogue clients are going to connect and interact with these services. Or if they did, they've made faulty attempts to lock down the service. So a few months ago, I found a privilege escalation bug in Checkpoint's ZoneAlarm antivirus. It has a service called Checkpoint Sandblast Agent Updater service that has a name pipe service that can be accessed by unprivileged local users. And the service can be used to trigger a call to a method called execute installer, which will just run an arbitrary exe as system. So it's not too far off from the runme method that we just looked at. And the way I found this, I Googled for best antivirus, and this was in the list, so I know it's one of the best. I ran the one-liner, and it started a bunch of services, actually. It started 4 unique services. So far, the only one that I found to be exploitable was this SBA Sepoya service host. And then I decompiled each service and looked for a reference to system.service model. After that, I started looking for exploitable functionality. And Method names are really helpful. Again, it's so nice that these things compile into source code with the names and everything. It just makes it a lot easier to understand what's going on. And so I saw a method called execute installer that sounded very interesting. Again, it'll run an arbitrary exe as system, and it's based on a client-supplied argument. So once I saw that there was some juicy behavior there, I needed to figure out how to connect to the service. And so the service endpoint definition is inside the onStart method, and there are 2 name pipe endpoints that get established. And they're also calling this add secure WCF behavior on the endpoint, which was a clue to me that they had done something to try to secure the channel. This was one of the first ones I looked at. So as I was doing this, I started trying to build a client from scratch, kind of like how we saw in WCF service, but a lot of times that's not necessary. Usually there's existing client code sitting alongside the service binary in the install path. And so I found this sbastub.dll, which had everything I needed to actually connect to the service. So I created a new project, added references to that DLL plus all its dependencies, and I created this sbastub object. And I just used Visual Studio to tell me what methods could be called on that object. And so the first one I looked at was called register sbastub. And I liked this one because it just took a simple string as an argument, so that I didn't have to create any complex structures to interact with it. And also because I knew that if I successfully registered a stub, whatever that means, that it would end up in the logs of the AV. So I would have evidence that I had successfully interacted with the service. Unfortunately, none of my registrations were getting logged, and it took me longer than I'd like to admit to figure out what the problem is. But the name pipe server, it gets the PID of the client that's connecting to the service. And then from the PID, it gets the actual file name of the client. Once it has the file name, it creates this X509 certificate object from the client, and it calls verify on it to see that it's actually a valid certificate. So it validates the certificate. Then it reads the CN field of the cert into a variable called text. And then finally, it compares text to a string that says Checkpoint Software Technologies Limited. So it wants to know that it's a valid cert and that it's signed by Checkpoint. So that's why I couldn't talk to the service, because my client wasn't signed by Checkpoint. So I considered 2 possibilities to bypass the check. The first was to inject code like DLL injection into a legitimate Checkpoint binary. The other was to sign the exploit code with a self-signed certificate. After I posted this exploit on Reddit, James Forshaw pointed out a couple other possibilities, including one that I really liked, which was that the check uses process.main module to read the file name of the connecting process. And that method reads the file name out of memory of the client, which is under attacker control. So you could start the client and then modify that structure in memory to point to a actual checkpoint binary and pass the check that way too. So because I didn't know how easy it was to do self-signed certificates, I first went with the DLL injection, which sort of worked, but I had to disable a feature of the AV for the DLL injection. It would block DLL injection. So at the end of the day, I had to go with self-signed certificates. And I read an article by Matt Graber that pointed out that non-admins on Windows can trust root CA certificates. So that means with a few PowerShell commands, I can create a self-signed cert, trust it on Windows, and then sign the code with it. So I signed my exploit, and then I tried to register a stub, and you can see that the stub registration did get logged this time. So that's good. So now I could actually interact with the service. So once I was working, I started playing with a method called send command. It takes one argument, which is a string of XML called command XML. And this argument is received by the service's onCommand receive method, which through a chain of calls eventually passes the argument into execute installer. Inside execute installer, the XML gets deserialized into a couple different objects. One of those objects has a field that's a string called installer package path, and that's really the only thing I needed to pay attention to. And whatever exe installer package path is pointing at, that's what's going to get executed by this method. So the only thing is whatever program that's pointed to by installer package path also has to be signed by checkpoint. So again, I considered two possibilities. One was to DLL hijack a legitimate checkpoint binary, and the other was to use self-signed certificates. Again, because I was ignorant, I used DLL hijacking first. And that's viable, and that would have worked, but signing the code was cleaner and easier. So now I'm going to show you guys what that looks like. And I did not start my VM, so let me start my VM up here. I'll make this bigger. Okay, so first thing, we're going to create the certificate object with the CN set to Checkpoint Software Technologies Limited, and then going to export the cert to a file called fakecert.cir. And then we're going to import it. And this is the part that's kind of questionable about why can non-admins do this on Windows. So we get this nice warning that we can just click through. And then we're going to sign the exploit, which is the WCF client. And then we're going to sign the payload, which is the code that's actually going to get run with high privileges. And so we'll just take a look. I'm the user test right now. And if we list the local administrators, you can see that test is not in that list. So we're not already an admin. And I'm just going to do this. So when I run this, we should see a new local admin get created called ZoneAlarm exploit. And so we got him right there. So thank you. How am I doing on time? 6 minutes? 7 minutes? Okay. I'm just going to cover another vuln that I found just over the weekend, which is in some no-name software called PowerPlan by Questica. It doesn't matter that it's no-name. It's more just the point to see how this stuff works. And and it's a remote example. So this service establishes a NetTCP WCF endpoint, which can be accessed by unauthenticated remote users, and it exposes an operation called get process data, which you can access to get a connection string containing clear text database credentials. So I found this on a pen test. Nessus had reported an unquoted service path, which is a pretty boring finding from Nessus, but the service was called WCF blah 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 service, which caught my attention. So I was like, let me go analyze this. And First thing, I wanted to find out, again, we're in the onStart method of the service, and found out what the address was, net TCP, and then a public IP address. Public meaning not loopback, so it was on a LAN, it wasn't internet exposed. And then the port is 8000 and the path is my service. We're using net TCP binding with security disabled. I found client code in DLL called powerplanclient.dll, and it defines a class called service interface client. So the class implements the methods defined in the iService interface interface. And you can see get process data is the one that we exploited. So I added references to the service DLLs. The constructor for the service interface client wanted the address and binding as part of the arguments. So I had to define those myself, and I had to set the security mode to none in order for it to work. And this is the entire exploit right here. So I defined the address, defined the binding, I created the service client object, and then I just called get process data on it, and inside that is the connection string. So, also part of the constructor for the service interface client was a service interface callback class, which you'll see sometimes they want these callbacks, and the callback is only defined as an interface. So again, I just had to do stub implementations for all the interfaces methods, which Visual Studio will do for you automatically. And this is what it looked like, heavily redacted, but I got the name of the database server that it was connecting to, as well as the username and password. I was able to then go log into the database. I didn't get any XP command shell though, unfortunately. So in conclusion, .NET decompilation makes static analysis easy because we get source code. We're exploiting the application logic versus WCF itself. Developers don't seem to be considering that we're going to interact with their services, or if they do, they don't secure it properly. And WCF, like I said, I haven't heard a lot of people talking about it, so I hope that this talk, you've kind of learned how to do it and can go out and find your own bugs. And that's all I got.
So we have a couple minutes for questions. Does anybody have any, or either here or online, if anybody's listening in?
Quick, easy one. For the network communications?
Yes.
Does the WCF have like encryption support? I think you touched on it, but I was distracted.
It does, and it's default actually to use TLS to transport the messages. Yeah. Yes, sir. I believe there is. I haven't. I've only I scanned one with Nmap the other day, and I forget exactly what it says, but I think the answer is yes. So.
Any other questions? Cool. Thank you very much, Chris.